All right, welcome back from break. This is what I'm calling Strange New World. My daughter Adine, who goes to the University of Tulsa, has agreed to do some video work for us. She's going to wave.
Hi.
And she told me to tell a joke to get started. The joke is, what did one titrant say to the other titrant?
Meet you at the end point.
Thank you. Family sense of humor. All right. I mentioned this in an email and posted on Blackboard, but here's the plan going forward that we're going to try and use. I'll be recording some lectures with the help of people like Adine, or I could narrate a PowerPoint, but I wanted to try a video lecture first. I'm going to put this on YouTube. Obviously, if you're watching this, you're on YouTube. And then that will give you the chance to pause the video anytime you want and try some problems and work on your own time. If you don't have your materials with you, please go to the website, Blackboard. And I've uploaded these as PDFs. These are the notebook files. And then I have the textbook chapter PDFs and solutions on Blackboard for free. And I'm really going to try and focus you on the most important problems. You'll get a short list at the end of part one here. And then I'll try to be on Zoom for office hours. And testing will most likely be built around Blackboard. We're already doing that. And then I may do some other homework assignments. So the first material we're going to cover is actually part of chapter 16. The early part of 16 was on buffers that we did right before break, but this material is just a couple sections, and it's about KSP. The SP, as you'll see, stands for solubility product, and it describes compounds that don't dissolve very well. Here's an example of something that doesn't dissolve well. That's a picture of a kidney stone. To start the chapter, I have two review problems from earlier in the class for some material that could potentially come back on us. And so at this point, I would say, please hit pause on the YouTube video and then try this problem on Le Chatelier's principle because it comes in this chapter. And so hit pause for a moment and then I will reveal the answer when you play the video again. So in this problem, the question asks, if it's at equilibrium, what will happen if you remove some of this cobalt chloride? And we know from Le Chatelier's principle, if we remove a product, the reaction will go forward. And so the answer for this one is the reaction goes to the right. And we'll see this idea a little bit. Here's a review problem on acids and bases. So once again, hit pause on the YouTube video, and then I'll return with the answer. So in this review problem, it states that this reaction proceeds to the right. So what statement is true? You'll see this a lot if you take organic chemistry. A standard rule on acids is that the weaker acid always forms. So in this problem, there are two acids. So if the reaction goes to the right, then water is the weaker acid. So that's the true statement. Reactions always tend to go the direction that forms the weaker, more stable acid. And so now we'll get into this material on 16.5 and 16.6. We'll review some of the basics on KSP. Keep in mind, SP stands for solubility product. We'll We'll be doing ice charts. We'll do some applications. We'll look at this thing called common ion effect. pH and solubility is actually one that we're going to skip for time and simplicity. So this one actually we will not do. And then we'll look at precipitation, making something fall out, just like rain falls out of the sky. You make a solid fall out of a solution. And so here's a big picture question to think about solutions. You'll have this picture in your notebook. And so label each of these beakers with the correct letter. So put an A, B, C, D next to one of the beakers. One choice will not be used amongst the three. So ask yourself, which of these is an unsaturated solution of sodium chloride? Which is a saturated solution of AgCl, and which contains the other ingredients? Like I said, one letter will go unused. And so hit pause again, and then I'll come back with the answer. So when you're choosing the beakers here, B will actually be the unused letter. Because when NaOH dissolves in water, it makes an Na and an OH ion. And so there's nothing in there that has any ions with two pieces. And so, beaker-wise, when we look at choice A, that's the middle beaker. Because that's an unsaturated solution that contains sodium and chloride ions. The first beaker has a molecule in it because it did not break up into ions. So this is C. And so the last choice has to be D. We know that's a saturated solution for sure because it has some solid material sitting on the bottom of the beaker and has a few ions in it. These are the kinds of compounds that we will focus on this section. It's poorly soluble materials. We're going to see AgCl is a poorly soluble salt. We won't be talking much about compounds like sodium chloride because it's extremely soluble. And here's a chance for you to use some of your background. I'll show you the answer in a moment. But what I want you to do is write the process or reaction, if you want to call it. But be careful not to make too much of a reaction. Take the compound calcium fluoride, and as a hint, I'll ask my camera person if she remembers the formula of calcium fluoride.
CF2.
Excellent. And so take calcium fluoride, solid, and dissolve it in water. Don't do any fancy reactions with the water. The water is just the place where it happens. So hit pause and try to write the chemical reaction where calcium fluoride solid makes ions in water. And so that's the reaction that you should have written. Calcium fluoride is a solid, and then it's in equilibrium with calcium 2 plus ions, and then of course it makes 2 fluoride ions. When we do some problems in a few minutes, we will actually be doing an ice chart, and so generally we'll be writing reactions and then doing the initial change equilibrium. here's a picture that is not in your notes booklet. What it shows is this idea that this is in constant equilibrium. There's some solid on the bottom in this beaker with water, and then there are some calcium ions in there. There are some fluoride ions, but constantly solid is being made and then it's being dissolved, and so this is in equilibrium. So now we have to think back to our K expressions. And so the same rules will always apply for this. The special symbol on there, SP, just simply means solubility product. When we did KAs, it was an acid. We had that special KW, that was water. This is just solubility product, and it deals with compounds that just barely dissolve in water. And so take a moment to write the KSP for the reaction that you have written for the calcium fluoride dissolving in water. And remember, as we saw way back in chapter 14, there's a special rule when you have a pure solid. So pause the video and then try yourself. So here's the KSP for this. There's a calcium 2+ ion, and then F-. We have to put a square on that because there's a 2 in the stoichiometry. Solids are not included in K expressions. So this is another reason this is called solubility product, because only the products of the reaction are in these K expressions. We'll see when we do the math, this greatly simplifies the math because you generally do not need the quadratic equation for these problems because there's no reactant where you're subtracting something. And so the math on these is fairly straightforward. These are very commonly seen if you end up taking exams like the MCAT, because some of the math can be done in your head on these. And so for pre-med students, this is a common topic you'll see in an MCAT study guides. And I just want to compare briefly some material way back from Chem 1. And so back in Chem 1, if you look at this on the screen here, this goes all the way back to page 147. If we looked at those solubility rules back in Chem 1, and we won't even go into those rules right now because we never memorized them. But when we look back at those, we were told at the time that sodium chloride is water soluble. Another rule back in Chem 1 is that any salt with nitrate is water soluble. I'm going to show the rules on the next screen, and I'm going to have you fill in the spots for the iron 2 hydroxide and the calcium carbonate based on the solubility rules from Chem 1. They'll be on the next slide here. And so pause the video when they come up on the screen or look back at your book and then determine if these two compounds are water soluble or not. So here's the table, so here's a chance for you to pause the video and determine if those two compounds are insoluble or soluble. so from the rules back in Chem 1, you should have found that this would have been labeled insoluble because it contains OH, is not an exception. This calcium carbonate also comes up as insoluble. And so back in Chem 1, we treated this as a yes or no question. We said these kind were soluble, these were insoluble. We're going to actually see this chapter. I'm going to fill in this far right for you. We're actually going to see this chapter. These compounds, like NaCl or sodium nitrate, these will actually not appear this chapter at all. I would compare these to strong acids. They dissolve completely, and so their KSP values will be very large. And so you won't see them this chapter. We won't really deal with them because they're water soluble. If we jump up to table 16.2, we actually see the iron 2 hydroxide in this table. We actually see the calcium carbonate in the table. This is on page 675 of the book. And these are the KSP values for these, for example, that we will be doing math on. You notice in the table, though, there's no sodium compounds. If you look over here in the S's, nothing to do with sodium. You won't find any nitrates in this table because those are all water soluble. They have very large K values. We're not dealing with them. So in a sense, you could say in Chem 1, we lied to you because we called these insoluble, but now we're saying they dissolve a very small amount, and we'll do some math on how much. This is not a question that's in your notes booklet per se, but I just added this in, just a quick concept check. I'm going to show you 5 compounds that are in table 16.2. And of course, these are values you never have to memorize. You'll have this at your disposal. But just pause the video in a moment and just looking at these values and thinking about ideas like strong and weak acids and solubility. What compound out of these 5 items would be the most water soluble? And then what compound from the list would be the least water soluble? So find the most and the least, hit pause, and then come back, and Adina and I will reveal the answer. So the most soluble compound, in a way that's analogous to strong acids, will be the value that is the greatest, highest from the list. So the most soluble compound from the list up there is the barium fluoride. So that's the most soluble, that's the biggest number on the list. The least soluble, and you have to watch your values here. We have 2 compounds with negative 10 exponents, and this is the smaller number. And so the barium sulfate has the lowest water solubility from the list. And so be careful on the exponents. The number out front, that just, you treat it as a positive number. number, so smaller number, smaller value. And so that's the least soluble of. And we'll be using these K values in a moment when we do some ice charts. And so here is our first ice chart problem on this. And I will get you started on this, but then I want you to finish the ice chart and then pause the video and then see the result on part A. So the first thing you always want to do with these problems is write a balanced equation to do your ice chart. So I'm going to get you started. Unless you think you can write it yourself, you can hit pause and check an answer, but I'm going to write it to get us going. So that's the balanced equation. It's going to make 1 Fe2 plus and 2 hydroxide ions. We'll use that to calculate the pH a little bit later. And then we do, just like before, ICE, remember, stands for initial change equilibrium. And I'm going to give you one more hint on this. Remember, when we deal with solids, they don't affect the math. And so in this one, this entire column is left out of the mix. And so I will let you try this problem, and then when you come back, I'll show the full answer. Or if you're not comfortable trying this one on your own, you can just let the video play and I'll work through it. So initially these values are 0 because we haven't put anything in water yet. When we do change, we pick a variable and then we put in a plus on these because the only way this can go is to the right. Some books use like a plus S for solubility. You can use any variable you want. Many people prefer X for algebra, from their algebra background. And so that'll be a plus 2x because we have to follow the stoichiometry. At equilibrium, this is X, this is 2x. We just follow down the column. And then we would say KSP equals X times 2x. And then that coefficient, once again, comes with us as an exponent. So algebra-wise, this is going to be x times the entire 2x squared. You have to be very careful about these parentheses, because then this simplifies to x times 4x squared, and so that will go to 4x cubed. So we can say KSP equals 4x cubed. And we have our number there, 4.9 times 10 to the negative 17th. Clean up this a little bit. And so we could say 4.9 The only problem with this touchscreen is it goes different ways on me. 4.9 times 10 to the negative 17 equals 4x cubed. You can see right away we're not going to need the quadratic in this problem, because We don't have any subtracted x's. And so then we just divide this side by 4. That'll go away. And then we take the cube root of that, and that will give us the value of x. And so on your calculator, you want to take the cube root of 4.9 times 10 to the negative 17 divided by 4. Make sure you divide it out first, and then you're going to solve for x. You can try that on your calculator, and then I'll put the number up in just a moment. When you do that operation-wise, the x value is 2.30 times 10, check my exponent here, times 10 to the negative 6th. That's x. The way we set up the ice chart, that's also the answer to part A. Because of the stoichiometry, there's a 1 here, and there's a 1 here, so that tells you that the value of x is the solubility of the FeOH2. And so that's the answer to part A. And the unit comes out to be moles per liter. So anytime we work with K values, the answer will come out to be moles per liter, capital M, molarity. Part B brings back some old material all the way back to chapter 15, which seems like a long time ago, especially with everything that's happening these days. And so this question is asking, find the pH at 25 degrees Celsius. And I'll let you try it, thinking back to OH and POH and things like that. So pause the video. You may have to look back in your notes on this, but try to find the pH at 25 degrees Celsius. And then when you come back, the answer will be shown. So in order to find the pH of a solution, you need to ultimately know the value of the H3O plus or the OH. And when we look at our setup up here, one of the products of the reaction is OH minus. And we have an X value here, 2.3 times 10 to the minus 6 moles per liter. The way we set up the ice chart, the amount of OH is 2x. And so we can say the OH is 2 times 2.3 times 10 to the minus 6. So the OH concentration is 4.6 times 10 to the minus 6. Then thinking back to earlier material, we can take the negative log of that to get the POH. Remember, pH is negative log H3O plus, POH is negative log OH minus. So depending on how you round things off, you should get a value very close to 5.34. And it's almost done because the problem is looking for the pH. And the reason I put the temperature on there is because at 25 degrees Celsius, there's an expression that we used a lot earlier in the course. It's pH plus POH equals 14. And then we can drop in the 5.34 for the pOH, subtract that from 14. And so the final answer for this, looking for the pH, is 8.66. Has to be above 7 because we're putting a base in water, we're making some OH. But it really effectively acts like a very weak base because it's not a very water soluble compound. If you put in something like sodium hydroxide, extremely water soluble, and the pHs are greater, it's a strong base. And so that's the pH of that, 8.66. So that was determining the water solubility from KSP. In the next sample problem, you're going to work the other direction. I'm going to do 2 problems like this. The first one will be pretty easy, and then the second one will have a twist or two in it. But it just involves some old skills that we know. And so this is asking you for the KSP of calcium carbonate. And it gives you the water solubility of calcium carbonate as 7.04 times 10 to the minus 5th. And so, just like we did earlier, start by writing a reaction where this dissolves in water. Don't react it with water per se, but just make ions. And so, I'm going to let you try this on your own. So this would be a good time to hit pause on the YouTube clip. And then when you come back, I'll work through the problem. So there's the balanced equation. Calcium carbonate makes calcium and carbonate ions. This is an ice chart problem. So we'll have the initial, change in equilibrium. We're dealing with a solid, so that won't count. We'll fill in just like the previous example. We'll put zeros here, because in this problem, there's no starting material. We put our variables in, we have one-to-one stoichiometry, so this is plus x. At equilibrium, x. And so this is, you'll see in a moment, this is as simple as these problems get. Because now, at equilibrium, KSP equals the concentration of calcium times the concentration of carbonate ions. They're both x's. So KSP equals x times x squared. The way the problem is set up, you're given the solubility of the calcium carbonate in moles per liter already. The units are the units you need for x. So this problem is simply 7.04 times 10 to the minus 5th squared. Punch in your calculator, and it should come out to be 4.96 times 10 to the negative 9th. In your book, you can check your answer on page 675, but it should be 4.96 times 10 to the negative 9th, because we're just squaring the value of the molarity of the solubility of the ions. Like I said, you can check the value right there, it has to be right. So in this first part of the chapter, we're just gonna do one more problem. And this is another skill type problem. It will involve an ice chart. It's pretty similar to the previous problem. It just has two differences. The stoichiometry will not be 1-to-1 because we're dealing with barium fluoride. And then you notice the units now are different. The units here are 3.21 grams of barium fluoride per liter. So those are the two extra twists in here. But beyond that, you're gonna write out the barium fluoride dissolution in water to make ions. You do an ice chart and just watch your units on it. So I am going to invite you to try this one on your own after you hit pause. The answer will be on page 675 of your textbook, so you can check there or check back on the video in a moment and I will work through the problem. So there's our equation. Barium fluoride makes 1 barium ion, 2 fluoride -1 ions. And then we'll do an ice chart where, once again, the reactant won't be involved. Initial, change, equilibrium. Put some zeros in there. I think you should hopefully start to see some patterns here. This is a plus X. Stoichiometry wise, this is going to be plus 2x. At equilibrium, we just add down the columns. We have an x and a 2x. So, just like we saw a little bit earlier, the KSP for this is going to be x times 2x squared. One of the most common mistakes that people that people make on these problems is that they forget to square the 2. And so remember, this is the whole parentheses. And so this is 4x cubed. And so in our calcium carbonate problem, the value of the solubility was given in moles per liter. This one has a different unit on it. It's grams per liter of barium fluoride. And so we need to get that in moles per liter. So you would add up the masses of barium and 2 fluorines off the periodic table. And let me check my notes. I want to get the right mass. That has a mass of 175.3 grams per mole. May have slightly different rounding, that's okay. It should be close to 175. And so in this case, once we get this value in moles per liter, that will be x, because the stoichiometry here is a 1 and a 1, and then that's our 1 on our x. And so we do a mole conversion, 3.21 grams over on the computer. Grams of barium fluoride, let me say 1 mole per 175.3 grams. When you divide that out, you get 1.83 times 10 to the minus 2. And so it's 0.0183. And so that's x. Because now it's in moles per liter. And so that goes in for X. Watch your math on this, because you put the X in the way we have it set up here. You have to cube it first and then multiply that result by 4. And I'll jump over the table on 675. That will tell you the answer you should get. And so, depending on how you rounded this, you may have a slightly different answer, but you should be very close to 2.45 times 10 to the minus 5th. As I've done throughout the year, I don't care about rounding differences, but you should be in that ballpark. If you have a very different answer, you may have accidentally cubed the 4. So make sure you do the cube first. It's 0.0183 cubed times 4, and then you get that for the barium fluoride. And so that wraps up really the first, almost 2/3 of this material on KSP that we'll cover. We'll just look at 2 applications coming up in the next part. And I'm really trying to focus you on the key book problems. And so, based on what we've done so far, if you understand these 6 problems, these 2 examples, this is a multiple choice on 683, and then these 3 longer problems, 57, 59, and 61. If you want more practice, the evens that go with it, 58, 60, and 62, are very similar. But if you understand these 6 problems, then you have the math down that we covered. We'll come back for a part 2 on the video, and then that will show us some applications. So you are welcome to try. I would encourage you to try these problems. You're always welcome to try my Zoom office hours. You can take a picture of these, and I can help you out if you're stuck on anything, or if you try some similar book problems like the even number problems. You're welcome to take a picture of anything, send it to me 24 hours a day. I'll probably get it too soon. And so I'll ask my director to stop the video.